Hello, and welcome to our talk on evaluating the explainers, black box explainable machine learning for student success prediction in MOOCs. My name is Vinitra Swamy, and alongside my collaborators Bahar, Natasa, Mirko, and Tanja, we're excited to present this work today as a collaboration from EPFL in conjunction with the University of Cagliari in Italy and Sharif University of Technology. With that said, let's get started. So, to motivate it a little, deep learning has been increasingly researched in digital learning environments. In the last 5 years of proceedings in EDM alone, we've seen countless applications of dropout prediction, knowledge tracing, auto-grading, plagiarism detection, and a plethora of other tasks that use neural networks for state-of-the-art research advances. However, these advantages come with a cost. Let's take the example of students who are participating in a MOOC on Coursera, and we predict their performance in the course based on certain behavioral features. And we identify that they will either pass or fail the course. Now, for student X, who is receiving a failing prediction, the most important question is why? Which features could I have worked on to improve my performance from a failing trajectory to a passing trajectory? In fact, can I trust the model's prediction at all if it's using some arbitrary features and not ones that make intuitive sense to us as educators to use? And so we see a problem. Deep learning here trades transparency and insights into which features are important for accuracy. Neural networks are pretty much a black box. However, they are able to capture these very complex and interesting data relationships, especially because we use this intensive time series in most of our applications in the machine learning for education space. However, they lack the transparency and interpretability of a traditional decision tree or SVM or linear regression or any traditional machine learning algorithm pretty much. Now, in our specific subfield, identifying why is actually very important. So we can kind of address these learning outcomes and learning trajectories to take a failing student and put them back on the passing student trajectory. We need effective personalized interventions, which can really be done by answering that question, why did the model make that prediction? The solution to this is a new field in machine learning called explainable AI. It's been a topic of much discussion in the last 5 to 7 years with a lot of different methods that are all targeted at answering this question of why did this model make this prediction, or how can I explain my model's actions? Now, while this field is new, there has been minimal related literature in the machine learning for education space because of its high applicability, of course, in these human-centric fields. We've seen SHAP for student dropout, LIME for student advising, and various other tasks. But the main insight here is that in each of these papers, pretty much only one explainability method is used. We have not seen a systematic study comparing explainability methods for applied machine learning fields, specifically in the education domain. So the objective of this paper is to address that gap. We want to evaluate the strengths and weaknesses of explainable AI methods across 5 diverse MOOCs and 5 different explainability methods. Our dataset is 20,000 MOOC enrollments for students with hundreds of thousands of student interactions. They are offered by our university in Switzerland, EPFL, which is a very large and well-reputed Swiss university, on Coursera as a learning platform. Now, with this objective in mind, we aim to address 3 main research questions. 1, how similar are the explanations of different explainability methods for one specific course? 2, how do explanations quantitatively compare across courses? How can these methods compare with each other? 3, do explanations align with prerequisite relationships that make intuitive sense to us in course curricula? To address these, let's dive into our larger pipeline. We have 4 main stages: data preprocessing, feature extraction, model building, and of course our explanations. We will address each of these in more detail in this presentation. Let's start with data preprocessing. As mentioned, we have 5 main courses, specifically digital signal processing 1 and 2, Ville Africain, Geomatique, and microcontrollers. These were each chosen for specific reasons, specifically for their amalgamation and diversity, as well as, if you notice, we have 2 DSP courses, 1 and 2. They are different in interesting ways. The first one is offered to bachelor students in French, and the second one is offered to master students in English. And they are taught by the same pretty much teaching team with the same curricula. So we expect these courses intuitively to have very similar feature importances to each other. Ville Africain is a humanities course on the design of African cities. Geomatique is a math course. And microcontrollers is a core engineering course used in a lot of the different engineering disciplines and certificate programs. The languages vary between English and French, with student levels in bachelor's and master's, as well as a wide variety in numbers of students from 500 to the 5,000 range. We have a variety in the number of weeks, and specifically a large range in pass ratio, where we look at courses with 5% as well as courses with 45% passing, and a wide variety in also the number of quizzes. Ideally, these features from these courses that are from these very different populations should find different aspects of the course very relevant for student prediction. In terms of our data, we have click streams of the granularity of when a student pauses and plays a video, what problems they click on, what their submissions are, etc., for each of these 5 courses. Now, there is a big dropout problem in MOOCs in general, specifically in the first few weeks of a course. We often notice that there are students who enroll in the course aspirationally and never participate, or wanted to watch one video and never complete any of the assignments and are definitely going to fail the course. And an educator can pick them out very quickly from these behavior patterns. So we determined that it's not actually a great idea to feed them to a very complicated neural network when we could just take simply their assignment scores from the first 2 weeks, feed them into a traditional logistic regression model. And those which are logistic regression model has 99% confidence in failing the course, we drop out of our training set for our larger machine learning tasks. This has 2 benefits. One, it values students who are actively participating in the course and allows our model to train more efficiently, focusing on students that have real interactions in the course already. So now we move on to feature extraction. From this click stream of video and problem interactions, we extract 45 different features. All features are derived from related literature, specifically from an EDM paper that our lab presented last year in implementing hundreds of features and then identifying in which environments, which features are most effective. We chose these 4 related works because in that work, they were found to be very predictive for MOOCs. They involve features like the total number of sessions the student has logged into, and for example, in regularity, how often a student views a video in the week that it is released, and tasks like this. We now move on to model building. So for these students, in our student performance prediction task, we have extracted 45 different behavioral features across 10 different weeks for our DSP course and various other weeks for our remaining courses. We feed it into a bidirectional LSTM model. We have experimented with a variety of different architectures as well. Our bi-LSTM performance is very, very well and very, very high, especially using a large number of data points from the course. And we predict pass or fail performance in general. Our objective is not to train the best model on our data. Our objective is to train a very good model so then we can have worthwhile and interesting explanations in the later stage of our pipeline. And now we move on to the crux of our experiments and explanation. We have a student, it feeds into our model. We have 5 different models for our 5 different courses, and we identify whether the student passes or fails, and now we're trying to identify the why. We have 5 methods: line, kernel shap, perm shap, CEM, and dice. We'll dive into each of these in more detail. But the key insight to keep in mind is the way we define an explanation across all of these 5 methods is how important is this feature to the model's prediction. We are identifying explanation in terms of feature importance scores from a specific instance. For a specific student, why did they get this specific prediction? So now we go to line, which is arguably the most popular explainable AI method in recent years. The way line works is as such. We first pick a specific point to explain. For student X, they have ending up with prediction Y. So student X failed the course according to our predictive model, and we have Y. Now we're trying to figure out why exactly this model made this prediction. To do this, we take our original instance and we perturb it by adding a little bit of noise in each of these different feature areas to create a lot of these different neighbors. We then take these neighbors and feed them into our black box model to get passes and fails. Essentially, we're taking our original instance, we're varying it in a lot of different ways, and we're seeing how the prediction changes based on those variances. We now have our X prime students, our neighbors, and our Y prime students. And using those, we can train an interpretable model, let's say a decision tree, on each of these neighbors and their eventual predictions. Using this, we can have interpretable insights, and from those directly feature importance scores for each of these different features for each student, average across all the students of a course. We then move on to SHAP, also a very popular explainability method. SHAP explains a student by quantifying the contribution of each feature to the prediction. What this means is it's trying to identify a score for the feature in relation to the prediction of how important it is. So we have X student fails the course with label Y. And let's say for student X, we had 3 features: number of minutes watching videos, number of clicks on problems this week, number of sessions overall. Now, to determine the importance of feature, let's say F3, we can create a model just using F3 and seeing how good the prediction is or whether it changed the prediction. But we'd also want to see it in conjunction with every other combination of features, which is called a power set in mathematics, or a coalition here. So we look at all of these different 8 combinations, and we see that it spirals very quickly. With only 3 features, we already have a cardinality of 8. We can imagine with our 45 features, what's going to happen in terms of the speed of SHAP. So we train a model on each of these subsets of features. And then we want to identify for a specific feature, in our case, F3, what is the marginal contribution of this feature? How did this feature change the predictive result? To do this, let's look at a specific example. Let's look at model number 2, which just uses feature 1, and model number 6, which uses feature 1 and feature 3. We see that feature 3 is added in feature 6. And so we can find the difference in the prediction between model 6 and model 2 is the marginal contribution for feature 3. Now, this is not the only case of this. There are 3 other cases in this model. So we need a weighted sum of these marginal contributions. And using this, we have 2 techniques. One, we have kernel SHAP, which is probably the most popular SHAP, which uses a kernel function to optimize this process of identifying weights for each of these different models. And 2, we have permutation SHAP, which really computes a forward and backward pass over all of these different features using antithetic sampling. They're quite similar to each other. They're trying to approximate the same thing, but they go at it in slightly different ways between kernel and permutation SHAP. So intuitively, to us in our results, both of these SHAP methods should be close to each other in feature importances. We then move to CEM, the contrastive explanation method. CEM attempts to find either pertinent positives, which is a neighbor to our original data point, with the minimal subset of features that should be present and whatever their values should be, or pertinent negatives, a new point, X prime, that is similar to our original instance, with the minimal subset of features absent to maintain the prediction. And you can see certain features should be absent, certain features should be included. We choose to use pertinent negatives for our calculation because they're most similar to counterfactuals, which will come in the method right afterwards. And to change this new point, X prime, that is generated through our CEM method into a feature importance score, we essentially take the absolute difference between this new point that is which essentially is all of the minimal subset of features that are absent. And we subtract it from our original point, and then we take the absolute value between those changes for that feature, and we multiply it by the standard deviation of the feature to essentially get how important that feature is to the prediction. Because essentially in the pertinent negative, whatever is left in this new generated point are valid and interesting features for, and essentially important features for our model at different weights. Okay, last explainability method. We look at diverse counterfactual explanations, or the DICE library. Essentially, we are trying to find a point with the smallest possible difference to our root point that results in a different prediction class. So if our original prediction was failing, what is the least amount of difference that will make it into a pass? We do this through 2 technical concepts, the optimizing the DICE loss and the DPP diversity metric, which are details, but essentially we can use the same process as CEM to convert these into feature importance scores. And from there, we dive directly into the results. We have our 5 explainability methods, and now we're trying to see for a specific course, let's say DSP1, how similar are the explanations of these different methods. What we see is that Lime is drastically different. It is very sparse in comparison with the remaining 4 explainability methods. We see on the y-axis a subset, of course, of all features, because we would normally have 45. These are based on the 5 features that each method found most important, and the union of those, which you can see is 13 features, which is not that many. So you can see that some of these features are definitely used a lot across different explainability methods. On the x-axis, you see the number of weeks for DSP1 and how important each method found those features in each week. You see kernel SHAP and perm SHAP are pretty similar to each other. CEM is pretty drastically different than the remaining 3 methods, SHAP, both SHAPs and DICE. So moving forward, how do explanations quantitatively compare across courses? For this, we use one metric called Jensen-Shannon distance, which is used to measure the distance between probability distributions. And what we see for each of these courses, on the x-axis is each method, and on the y-axis is also each method. So we're trying to find the distance pairwise between methods using Jensen-Shannon. What we see is on the diagonal, of course, zeros, because the distance between lime and lime would be 0. But for lime in every other case, we see a bright orange, which means that it is very different. The distance is large between every other explainability method. The other thing that is interesting is intuitively, both of our SHAP methods have this kind of box in the center where it's quite dark, so the distance is small, which makes sense to us. Continuing forward, how do explanations again quantitatively compare across courses? We also use Spearman's rank order correlation. So instead of looking at the distributions of feature importances, we say for each method, rank the features in their importance and compare these rankings with each other instead of the raw scores. What we see is, of course, on the diagonal, they're all ones because they are exact matches to themselves. But we see lime is quite drastically different from the other explainability methods. We again see this box in the middle between kernel SHAP and perm SHAP. But dice, CEM, and lime are quite different from each other, definitely. Essentially, looking at these plots, we see similar relationships also across courses, which points to trends that go to explainability methods and not to courses directly. And that dives us into our next result, which is a PCA analysis. We took the feature importance distributions from each of these methods and graphed them on using PCA. I think this is the most interesting graphic of this whole presentation because what it shows is each of these symbols represents a course. What would intuitively make sense is all of the symbols of a course come close together because the model and the data are both based on the exact, they're both the same model and the exact same student data points. However, what we see here are clear clusters by explainability method and not by course. And what that entails is a result that shows that explainability methods themselves are a bit biased and are impacting the results of the feature importance scores more than the model and more than the data. Now, to validate these results, we see that there is clearly a disagreement problem here between a lot of these different explainability methods. We've seen it across Jensen-Shannon distance, we've seen it across Spearman's, we saw it across the PCA analysis. So can we intuitively find some way to make sense of which explanations are more valid for us? For this, we talked to the professor Paolo Pordoni, who taught DSP1, and he worked with us to create a skill map of when in the course which skills are taught and which skills are prerequisites for other skills. And so we came up with a game plan, which is we can train a model just to predict the student's performance on week 5 based on the same features that we had before. Now, we know week 4 is a direct prerequisite to week 5. Can we examine if our model found week 4's features important? And what we see here is week 4 is pretty important across 3 representative methods. We choose line, one of the SHAPs, and one of the counterfactual methods to look into this analysis. And week 4 is important in both perm SHAP and CEM specifically. However, each of these methods find different features important. We repeat the experiment again for week 9, and week 9 has a lot of different dependencies across the course. And what we see is pretty different feature distributions for each of these methods, although of course each of them find that the features of the behavior in week 9 do correlate with the performance in week 9 as well as a pretty even distribution across a lot of these different features. So what are the implications of this work? Explainability methods in general are imperfect and biased. We urge data scientists to carefully select their appropriate explainability method based on their downstream task, and to also be aware and acknowledge the potential biases of these explainers while analyzing your results. And the extensions, of course, are to extend this to different tasks and modalities. This was, of course, one task, just student performance prediction on just MOOCs. We want to see if this holds true, this disagreement problem in explainability across a lot of different settings. We want to explore different architectures beyond just file STMs to see if the explainability method effectiveness differs across predictors. And lastly, we want to find out which explanations lead to the most effective interventions for improved learning outcomes. Maybe we can assess quality of an explainer in this way. But the main takeaway from this paper is this one sentence. Explainability methods systematically do not agree on which features are important for predictions. For the same courses, for the same models, for the same points, we saw that our 5 methods disagreed with each other. And using our insights, educators can hopefully be aware of the bias of their chosen explainability technique and address this in the future. We release our code on GitHub, open source,